next example, we have a product. So if we multiply out or FOIL out the terms, then we can solve them using the basic rules. So we have x times x to the half minus x times 2 over 5x plus 2 times root x, which is x to the half, minus 2 times 2, which is 4, over 5x. We want to integrate that all with respect to x. So we can separate them into 4 separate integrals. In the second term, we can cancel the x. We have minus 2/5 integral of 1 with respect to x, plus 2 times the integral of x to the half with respect to x, minus 4/5 integral x to the minus 1 with respect to x. So for the first three, we can use the anti-power rule. So the antiderivative for x to the power 3 over 2 will be x to the 3 over 2 plus 2 over 2 is 5 over 2. And you can divide by the fraction 5 over 2, or I will multiply by the reciprocal 2 over 5, minus 2/5. The antiderivative of 1 is x, or you can think of it as x to the 0, so it'll become x to the 1 over 1. Here I'll just write x, plus 2 times the integral of x to the half. X to the half plus 1 is x to the 3 over 2. Instead of dividing by 3 over 2, I'll multiply by 2 over 3, minus 4/5. And just remember that x to the minus 1 has its own antiderivative rule. The antiderivative is ln of absolute value x plus c. So at the beginning, we had a product, which is in a basic antiderivative form, and we multiplied it out so we could use the basic rules. In this antiderivative, again, we have a sum. The first term is a basic form, but the second term we'll have to divide by x to separate it into the basic forms. So I will separate it into 3 integrals. 4 times the antiderivative of 1 over 1 plus x squared plus x sine of x over x minus, in the numerator, x is cubed and 5th rooted. So it's the antiderivative of x to the 3 over 5 over x with respect to x. So the first antiderivative is arctan x. Next we can cancel the x and x in the second term. So we just have the antiderivative of sine x. In the third term, we're dividing by x to the 1. So it will be x to the 3/5 minus 1. So x to the 3/5 minus 5 over 5 is x to the minus 2/5. The antiderivative for sine x is minus cosine x. And x to the minus 2/5 plus 1 is x to the 3/5 divided by 3/5 or multiplied by 5 over 3. So in this example, to be able to use the basic rules, we first divided the terms by x. The next example, again, we have a product. To use the basic rules, I will multiply out cosecant x to both terms in the bracket. Next, I will separate them into 2 basic integrals. We can take the constants in the front and separate the integrals. So both of those are basic rules, so we can integrate them. So the antiderivative is negative 3 cosecant x plus 8 cotangent x plus c. In this example, we can separate it into 2 basic integrals. 8 times secant squared x dx minus integral 2 to the x dx. So we equal to 8 times tan x minus, here we have an exponential function where the base is not e, so we'll just divide by ln of the base. So we have 2 to the x divided by ln 2 plus c, and that is the antiderivative. Again, I'll separate it into the basic forms. Here I will pull out these fractional constants. So we have 3 over 10 times the antiderivative of secant x tan x plus 2/5 times the antiderivative of x to the minus 1. I'll rewrite it as 1 over x, square root x squared minus 1. And now we can use the basic rules. So we have 3 over 10 secant x plus 2/5 arcsecant x plus c. The following problem is about our nearest neighbor in space, the moon. A hammer and a feather fall with acceleration a of t is equal to minus 5.2 feet per second squared from a height of 5 feet on the surface of the moon. Given that v of 0 is equal to 0 and s of 0 is equal to 5 feet, a, determine the position as a function of time, and b, how long does it take to fall to the moon's surface? So for part A, we are given the acceleration function, minus 5.2 feet per second squared. This motion is along a straight line, so we will use that the acceleration function is the first time derivative of the velocity function, and it's also the second time derivative of the position function s. So we can take the antiderivative twice to solve for the position function s. We'll also use these two conditions, v of 0 is equal to 0 and s of 0 is equal to 5, to solve for the constant c. To find the velocity function, we'll take the antiderivative of the acceleration function with respect to time. So we have the integral of minus 5.2 dt, which is minus 5.2t plus, I'll call the constant c1. To solve for the value of c1, I'll use the condition v of 0 is equal to 0. So 0 is equal to minus 5.2 times 0 is 0 plus c1. So c1 is 0. So the velocity function v of t is minus 5.2t. Next, to find the position function s, we'll take the antiderivative of v with respect to time. So the antiderivative for minus 5.2t dt will be minus 5.2 is just a constant, and then the antiderivative for t to the 1 is t squared over 2 plus c. So again, we can solve for c2 using the condition that was given in the problem. They're falling from a height of 5 feet, so s of 0 is equal to 5. So 5 is equal to 0 plus c2, so c2 is 5. So the position function is minus 2.6t squared plus 5. For part B, we want to find out how long it takes to reach the lunar surface. So in that case, we want to find the time t when s is 0. So we'll set s of t equal to 0 and solve for t. So we can subtract minus 5 and then isolate t squared by dividing both sides by minus 2.6. The two negatives will cancel out, and t squared is equal to 5 over 2.6. Then we can solve for t. We're square rooting a square, so it's plus or minus the square root of 5 over 2.6. But in this problem, we will only consider positive t. And if you calculate this in decimals, it's around 1.4 seconds for the hammer and feather to reach the lunar surface. In the 17th century, Galileo wrote that all objects, regardless of mass, would fall at the same rate in a vacuum. And next up, here is some footage of the hammer and feather experiment from the 1971 Apollo 15 mission to the moon.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings. Superb.